Thanks, everyone. Sorry for that short delay, and thanks for your patience. Welcome to track one. Welcome back if you were with us for the keynote, and welcome if you've just joined us. I'm Jonathan Starr. I'll be the host for the rest of the afternoon on track one here, where we've got some great speakers and presentations coming up. So again, just as a reminder, I know many of you are already doing it. Please use the stage chat feature to ask any questions or put any comments in. It's just been a great way to make sure that we've got a measure of where your levels of interest are and the questions that you've got for our speakers. So please continue to use that as we go through the afternoon. So in a moment or two, I'm going to introduce our first speaker of this afternoon. We're going to hear from Esther Yu. Esther's a professor of residence at the University of California, San Francisco, where she specializes in using imaging technologies to diagnose and treat disorders of the brain, spine, neck, and other parts of the central and peripheral nervous systems. She's going to be talking to us today about the challenges and solutions in the development of an AI for medical imaging. So without further ado, I think we're ready to hear from Esther. Esther, thank you so much for joining us this afternoon. We look forward to your talk. And again, for everyone who's listening in on this, please, any questions that you have, put them in the chat and we'll get a Q&A going at the end. But for now, Esther, over to you. Thank you.
Thank you very much for that introduction. Hi, everybody. Good afternoon, and thank you very much for coming. So today I'll be talking about artificial intelligence for medical imaging. So the ever-growing use of medical imaging means that physicians, known as radiologists, are now evaluating many thousands of images in a single workday. And this really now is beginning to outstrip the human ability to thoroughly look at each individual image. So today in this talk, I'm going to describe some of the challenges and solutions that we had in the development of an AI through close collaboration of UC Berkeley computer scientists with doctors at UCSF, including myself. And we came up with a system that does rival experts at the relatively narrow task of interpretation of head CT scans. This is a very common medical imaging study. Disclosures, so we did just a few months ago have a US patent granted for deep learning for CT imaging of neurological emergencies, and that's assigned to University of California Regents, which is our employer. The problem is that, as I mentioned, in medical practice, radiology is becoming ever more central in the process of patient care. There's an increasing number of studies being ordered. There's an increasing number of images per study because they're getting more complex. And the number of studies and images that a radiologist is asked to interpret in a typical workday has been growing steadily over time. When I was a resident trainee in the early 2000s, we could actually look at each individual image at that point. There was something on the order of many hundreds of images per 8-hour workday. And you could actually go through each image and actually look at it in, spend like a couple of minutes looking at an image. Nowadays, there's literally thousands of images that each radiologist has to evaluate himself or herself in a single day. And it's become at the point where you really cannot. And, we now have these the scroll wheels on the mice that you can just spin it and the images kind of fly by like a movie. And it's essentially you have to do that in order to actually get through the workload through the day. And there's not really an option to slow down because patients are always arriving in the emergency department and need interpretations of their studies very quickly. The increasing number of studies per radiologist and then images per study is a problem. In addition, lately, something you may not have heard is that there's been a real push for radiation dose reduction. These CT scans do involve radiation. It's not a huge amount of radiation, but if you have many, many scans per year or throughout your lifetime, it can add up to a significant amount. So there's been a significant push toward radiation dose reduction, and that has introduced an additional problem in that the images are noisier and are even more difficult to interpret, so require even more specialization and expertise to actually interpret correctly. So this is a CAT scan of the head. Computed tomography is the formal name, and this shows an image of the brain. We read thousands and thousands of images like this per day, and it shows the brain. The white part is the skull. and this black in the center is called the ventricular system. These are all normal structures. This image is actually has a very significant abnormality that needs to be picked up. So the abnormality is actually here. It's in red. There's a thin layer of blood layering against the brain, over the surface of the brain on this side. And looking in retrospect, you can see this sort of shaggy area here. It looks a little bit shaggier than the kind of more straight margin of the skull, or the more well-defined sharp margin of the skull. It looks a little fuzzier. This is actually called a subdural hematoma. And this is a life-threatening emergency. It has to be picked up. Without picking this up, the patient would be sent home, and possibly this could expand, throughout the time they're home, and within several hours to a few days could be fatal. So this is the type of thing that we do every day. We look for this kind of abnormality. So 15 million people suffer a neurological emergency, particularly strokes and traumatic brain injury each year in the United States. And 80 million of these CT scans are performed each year just in the US alone, not to mention even worldwide. Head CAT scan is pivotal in evaluation of these neurological emergencies. This is the workhorse study that everybody gets. If you come to the ER with a brain problem, this is what you get. You don't get MRI, you get a CAT scan because it's super fast. They can just put you right in the CT scanner, and within a few seconds, they can get these images of the head. Currently, it takes about 5 minutes to an hour for a radiologist to interpret the study and then send or transmit those study results to the emergency department. So now I'll switch a little bit to the topic of deep learning. So many of you are probably very familiar with this area, but in a nutshell, this paper by Rumelhart in 1986 is a classic paper that proposed the idea of a neural network that would consist of neuron-like units that were modeled after actual neurons in the mammalian visual system that could solve tasks such as recognition of features and images. It was not, however, until over 10 years later, when this other classic paper, 1998 by Lacuna et al., applied this to a real practical problem, which was the recognition of handwritten digits, so digits written by humans, and showed that it actually could work and be, pretty accurate. So there was an over 10-year gap between kind of the concept being introduced in this paper and then the actual practical application to a problem. After this, at this point, there was huge excitement about this. People kind of thought, okay, this is the solution to all problems. We could use AI and neural networks to solve all kinds of problems that we have, not just image recognition, but all kinds of problems that humans were not able to solve previously. So there's huge excitement, and people said, oh, this is going to be the answer to everything. Unfortunately, in the 1990s, there was the so-called AI winter, when the hopes and promises of those early results with the digit recognition really were not able to be translated to more complex problems that required more general intelligence. So, this is a quote from, so we were promised thinking machines and all we got was automated number recognition for ATMs. So this was actually implemented as a result of the earlier work, and, handwritten checks, like signatures and digit recognition was implemented at ATMs. And so that became, very practical application that was widely deployed. So that was good. But in, this idea, this, fantasy of, initially the fantasy that we could solve all kinds of, human problems with these neural networks did not come to fruition. And this led to the so-called AI winter of the 1990s. I was actually, when I was a student, an undergraduate, some graduate students I remember actually left the field. They had already spent a couple of years in this area of neural networks, and they actually, even after spending a few years of their graduate career on the topic, they actually abandoned it to go on to something else because they thought there was no hope in progressing further. So that's the AI winter of the 1990s. So what happened in the last 5 or 10 years? So the things that happened since then that allowed deep learning to actually become more widely applied, and these neural networks to be applied to more complex problems. There are several technical developments. So first, hardware, relatively expensive, massively parallel computing power in the form of GPUs were developed. Software, so software libraries that were easier to use for these massively parallel GPU processing tasks, and network connectivity, and also much cheaper data storage were developed, so that with the rise of the internet, there were a lot more images that were available that you could just grab from the internet, images of cats, etc. Millions and millions of images that you could use to actually, and you can actually store them on relatively cheap hard drives and actually aggregate these massive data sets that were required to get a reasonable result, to train these deep neural networks to actually get reasonable results. So those were some of the technical changes that led to the actual more widespread application to more complex problems than just digit recognition. So back to our head CT. The CAT scan requires very fast interpretation for life-threatening emergencies, and it does require a high level of accuracy, even for tiny abnormalities, such as the one that was shown here. In addition, this is a single image. This CAT scan actually consists of a 3D stack of 30 to 60 images. So there's this image, but there's also many other images through the head, kind of slicing through the head. So all of those images have to be interpreted for a single patient to correctly classify. So if one image is normal, or 10 images are normal, and then 5 are abnormal, or even 1 is abnormal, you need to pick that up as a radiologist, because sometimes abnormalities only show up on a single image out of that 30 or 60 image stack. So that compounds the problem in that, unlike recognition of cats or dogs, something like that, in a single photograph, you actually need to correctly interpret a stack of images, which compounds the difficulty of the problem. Segmentation is another thing. So in addition to classification, it is actually very useful to outline the actual abnormality, the feature that's abnormal. So that's something that is very important because, well, you want to know what the computer is actually describing as abnormal. And you know, as Jitendra Malik, who's an EECS professor who we collaborated with closely, when we first started this project, one of his graduate students said, well, you know, you don't need to do this outlining of the abnormality, just interpret the stack of images as yes or no, abnormal or normal, and then you're done. So Jitendra said, he piped up at that point, he said, well, I don't know about you, but if it were me, I want to see the output. I don't want to just trust a yes or no. I'd like to see what it's actually finding, you know, to just make sure. So segmentation is actually, is so-called segmentation, where you actually outline the abnormality, is actually very important for confidence, for physicians actually using this information. This is one of our earliest results. Shows a large intracerebral hemorrhage here. It's mostly bright. It has a little fluid level because the red blood cells are heavier and they sink to the bottom, so it creates this kind of little fluid level. This is a kind of obvious hemorrhage that, you know, almost anybody could recognize this. If you saw a few examples, you could probably pick this up easily, like anybody, untrained eye, just by using symmetry. Something's wrong here, clearly. It's not symmetric. This is one of our earliest results, and it only requires really 100 or 200 training exams to get a reasonable segmentation like this. This is a radiologist demarcation, which is something I traced out by hand. And then if you train the network our initial attempts at a network at head CT interpretation, if you train that with images on the order of 100 exams or so, you can actually get a very good result here. This looks really quite similar to the demarcation by radiologists. And, you know, trained on just a few hundred of these cases, you could actually achieve, for these large, obvious hemorrhages, you could achieve a reasonable accuracy. This is a ROC curve, which a lot of you are familiar with. The area under the curve greater than 0.95 for recognition of pretty obvious abnormalities. So these are cherry-picked exams where there's pretty clear abnormalities. And so you can get this pretty nice-looking ROC curve. You know, 0.95 is a very respectable result for an AUC. But we have to remember, this is only for single images, and as you recall, there's 30 to 60 images in each head CT exam. So that creates a big problem because your accuracy is over 0.95 for a single image, but then if you are interpreting 30 or 60 images, that creates a big problem because then your overall accuracy for the exam is going to go down and it's going to be unacceptably low. A typical radiologist is expected to really not miss any hemorrhages. You know, if you miss one out of maybe a few hundred, a very small one, you can still practice and that's considered okay. But once you start missing more than one out of a few hundred, then, you know, it starts to be potentially a problem for everybody, the patient, obviously, and, you know, the emergency department, who's, you know, the primary caretakers of these patients. So you need to be very accurate. So in the end, how much data do you need to train the algorithm? So this was essentially, you know, the rest of the project consisted of two prongs. The computer scientists in EECS, Jitendra Malik and his graduate student, Wei-Cheng Kuo, and postdoc Christian Hain, they worked on the algorithm and tweaking it and tuning it to tailor it to this particular problem. And then, you know, the radiologists on our side, we actually segmented these scans, which is a very painstaking task, and you know, it's it's difficult to do because it takes a lot of attention, but it's, there's not a lot of thought going into it. It's just a lot of rote repetition of, very painstaking manual tracings. So over the course of this project, which was funded by the California Initiative to Advance Precision Medicine, we were funded, UCSF and UC Berkeley were funded to do this. We went ahead and segmented many, many thousands of these images, and I kept track of our progress over time. So this is essentially, several of us did this over time, and we didn't know where we had to stop in order to get a reasonable accuracy. But we kept on segmenting these things, and this is the number of images that went up over time, and over the course of this period of over a year, we reached 80,000 images, and some of them are normal, so those you get as a freebie. The normal ones are they're just normal, so quite a lot of these are normal. So keeping in mind 80,000, but probably 80% of these are probably normal images. But nevertheless, we found that it actually was necessary to actually segment that number of images. In the meantime, while we were busy doing that work, the computer scientists at Berkeley were working on the algorithms and tweaking those and identifying all the different parameters and refining them to try to improve the network. And Wei-Cheng Kuo, the primary graduate student, and the postdoctoral fellow Christian Hain, under Jitendra Malik's guidance, were able to introduce a number of innovations to try to tailor the networks for this particular problem. This is now independent of the data. The quantity of data is an independent thing. More data is always better. But this is more, this requires actual looking at a lot of trial and error in trying different conditions for the algorithm, different parameters, and trying to optimize it. And, the result was quite good. So, on the whole stack of images now with randomly selected CT scans, which is a much more difficult problem than interpreting a single image with an obvious abnormality. Now with randomly selected scans with the full stack of exams, Wei-Cheng and Jitendra and Christian developed networks with our data that could actually reach an AUC of 0.965 on entire exams. So we thought this is actually very good. So this is getting closer to what a radiologist's performance would be expected to be. In addition, the abnormalities that were detected, that we could detect, were much more subtle. Instead of that huge hematoma in the center of the brain, some more subtle abnormalities could be detected, such as this subarachnoid hemorrhage here, these bright streaks here, and this subdural hematoma. This is the radiologist tracing. This is what I traced as the ground truth, so-called ground truth. This is the original image. This is the computer predicted probability map. And this is the map when you cut off the probability at a specific level. You have to choose a level of probability to threshold the computer predicted map. But quite good when you look at it. There's not perfect matching, but it's actually quite good. And then the UC Berkeley, the EECS department, our collaborators, they came up with additional tricks such as identifying which types of studies were more important to actually manually trace in order to improve the network. So instead of just taking all the exams and manually tracing them, this was a paper that they put out with us, showing that if you can actually intelligently select the training data to spend most of your time on certain types of studies to actually be more efficient in training the network. So instead of training hemorrhages that it'll already recognize and is fully capable of already recognizing, this paper was describing how you could intelligently select the images that would be likely missed and would still need to be added to the already existing massive set of training data. This shows the DICE index, which is a commonly used measure of accuracy, and it shows our DICE index. So this describes the accuracy of the actual tracing of the radiologist versus the computer tracing of the abnormality. Radiologist to radiologist, about 0.7 to 0.8 is a good number. If you compare two different radiologists tracing a complex hemorrhage such as this, a DICE index of about 0.7 or 0.8 is the best you could expect, because even there's some subtle differences that even a trained eye would actually, there could be differences between expert radiologists. But over time, this is over the same time period of the grant, we were able to increase the DICE index up to something close to what we'd expect for human experts. And this is our final. So in the end, Wei-Cheng, who's now at Google, his final paper, this PNAS paper, a proceeding of National Academy of Sciences, showed our final result and we actually benchmarked it against humans. So these were 4 board-certified radiologists. 2 of them were one of them was a neuroradiologist, and shows their performance compared to the UC Berkeley BEST algorithm, in addition to our massive amount of training data that we collected. So this shows that we had a very excellent AUC now of 0.991, which is higher than the initial attempts. And in addition, these are for full stack interpretations, meaning the entire stack of CT images have to be interpreted correctly. And it shows that 2 radiologists are still above the curve and are slightly more accurate, and 2 radiologists came below the curve, so are less accurate than the computer. So he was quite pleased with this, and we were all quite pleased with this, because the CT scan, this type of study is, as you can see, it's very noisy. It's not a high contrast study. It's actually difficult to pick out subtle abnormalities, and so we were quite happy with this result, that it performed this well compared to trained experts. And these are just some examples of the abnormalities that were detected by the computer here. And this is the outline of the manual tracing by a neuroradiologist, and shows that it matches very, very well for some of these very complex intracranial hemorrhages. Just more examples here of some beautiful segmentations. When some of my radiologist colleagues saw this, there was a lot of fear, actually, just because the segmentations were so exquisitely done that it really looked indistinguishable from a human. So very, very excellent results in the end, with a combination of very good collaboration between our departments, and it was a great project, and we really, really enjoyed pursuing this. So in summary, the challenges to adoption. So we were able to do this for this particular specific task of CAT scans of the head interpretation. And we were very pleased with the results, but there's a number of things, that caveats that we always, that we still have to remember. Challenges to adoption, there's still a lot of problems. More large-scale validation studies are needed to show the performance of these algorithms in real-world clinical settings, meaning that you're not just taking studies that have done, retrospectively that have been done and then testing the algorithm. You got to actually take the thing and put it in the actual emergency department and actually run it. And there's all kinds of things that crop up that are kind of, one-off things. And, there's a very long tail of, strange things and, unusual images that appear. And those are things that you really can't capture in a research study. You have to actually deploy it in real-world settings and see how it performs. And then in addition, integration of the AI into actual clinical workflows is a challenge, because you need to make sure that it's actually, beneficial to the radiologist. You don't want an algorithm picking up all kinds of abnormalities, suspected abnormalities that are not actually there, because that actually make it harder for the radiologist, because they'll be scrutinizing each image when there's no abnormality on it, and they'll be, starting to see things there that are not there. So the AI has to be integrated in a good way, so that it actually benefits the patients and is not just not actually a burden. And so this is just a slide. It's this Amara's law, so-called Amara's law, which you may have seen. So the quote is, human level AI is always 20 years away. And then once something becomes useful and uncommon enough, it's not labeled AI anymore. So I think, probably with medical imaging, interpretation, this is going to follow a similar curve, So, we're still, we still have, lots of ground to cover in order to make these actual actually very practically useful. But eventually I think it will actually happen. So first there's an overestimate of what you can do, and then eventually it's an underestimate. And then finally, just remembering that deep learning can be extraordinarily powerful when trained for very specific applications, such as this. This is a very specific task. And so just keeping in mind that, even though it performed very well in this very specific task, and you can actually, use that to that information to kind of bootstrap other algorithms to train on similar tasks. Deep learning is far from being so far an artificial general intelligence, in that we can interpret head CTs specifically for specific abnormalities, but integrating with that with all of the clinical information and all the other information that you get about the patient, that is something that's a much more difficult task that requires general intelligence, and we are not anywhere close to that right now. So that's what myself and my colleagues, we think that there's still a long way to go in really optimizing this for actual patient care. And keeping in mind that every patient is very unique, and that the clinical information, it's not just the images, but the whole totality of information that you get about the patient. Even looking at the patient, seeing what the patient looks like, this is all information that comes into decision making. And so these things are sometimes swept aside when people talk about the excitement of AI for radiology image interpretation. We can replace radiologists with an AI that can do a better job and a faster job, perhaps, but that's not really everything that comes into the task. You need to really do the best job you can. You have to integrate all kinds of other information that's not imaging. It's other things that actually inform your actual interpretation of the images themselves. With that, I'd like to just thank the colleagues that participated in this project. We had some neurologists, UCSF Narissa Ko and Dr. Claude Hemphill, neurosurgeon Dr. Jeff Manley, who operates on these traumatic brain injury patients and provided some clinical expertise. Pratik Mukherjee, who's also a neuroradiologist and helped segment these exams. Wei-Cheng Kuo, who's now at Google, who was a student of Jitendra Malik in EECS department. And so I'd like to thank everybody for participating in this project. And thank you all very much for coming.
Esther, thanks so much. Really appreciate you presenting on that very important and interesting work. We don't have a lot of time for questions. Just to say that I don't know whether you've been able to access, Esther, as you've been going along. There have been some great questions coming in.
Yes.
Maybe the one I'll ask, which is probably essential at this stage in terms of there's a couple around how can we get access to this literature? Is it shared? Things like that would be I guess very important for people to know that they're clearly interested in finding out more.
Yes. So with our work, the PNAS paper, that's summarizes the results at that time. Things have progressed since then, but that is a good reference. But actually, since 2019, there's been really an explosion of work in this area. If you just look on an internet search of medical imaging and AI, you will find more information than you could possibly want to see. That a lot of people have glommed onto this for the reasons I was talking about, which is that radiology image recognition is sort of it's kind of a pearl of, it's an area of medicine that is really ripe, and it's ideal for neural networks because it's an image recognition task, and there's tons of people who've glommed onto this as like, okay, this is something I can solve. But so there's been an explosion of work in this area and excitement about this area. So our work, if you look at Jitendra Malik and my name and Pratik Mukherjee, you'll see some of our papers on this work. But really, there's just a ton of work that's been done since then. That's very, very informative.
Okay. Thank you. And you'll see in the comments there a number of questions, and I think you addressed this a little bit with the kind of the AI, AGI. A lot of questions about the generalization of this, just around, can it be used for other brain issues? Can it be used for other organs? Can it be used for other medical applications like surgical robots? So it's interesting to think clearly this one was very specific as you've described it, but anything to say just about generalizability?
Well, I would say that head CT recognition, although we were very pleased with the results, our end results, it is actually a very narrow task compared to surgery. When you think about surgical robots, what that has to do is it has to not just recognize the image, but it actually has to control the robotics to actually. So that is I personally think that's an infinitely more complex problem. It's more like self-driving cars or something, even more than that, because things in real time in surgery are really, there's a long tail of complications that can happen, and that's a much more complex problem. So I think, surgical robotics, it also ran into sort of a bit of a wall. My brother actually worked on this a bit. He's a surgeon, and there was initially a lot of excitement about AI with surgical robots, and I think, it will happen, and it's still progressing, of course, but it's just a much more complex problem that requires, I would say, much more general intelligence. If you're comparing it to something like particularly this problem, which is a very straightforward, in some ways, our task is a very straightforward image recognition task. So relatively simple, really, our task.
Right. Let me just ask you one final question, because there's a couple that come up around the data, the training data that you use here, just about the validation of it. And then also, do you find difficulties with things like HIPAA regulations playing a role in kind of obtaining and using training data here? Is that something you need to be kind of acutely aware of?
Yes, very much. So I talked to somebody who was in industry working on this problem, and he said that if it weren't for HIPAA, then they would have solved all these problems, and they could do all of this. And it's probably an exaggeration, but it's somewhat sort of correct. HIPAA is a huge barrier in this country to obtaining training data. We use training data that's retrospectively selected and de-identified, and that kind of training data, if it's de-identified, is considered. If you de-identify it in the correct way, it's considered low risk human subjects research, and so it is relatively easy to get approval from an institutional review board at UCSF, for example, to use images in that fashion. You have to have certain conditions. You have to strip the images of any identity. You have to keep them, secure, and just make sure there's no way to identify the patient that came with from whom the images came. But you can actually use these if you're in a university setting or a hospital setting where you have, you can actually do that. But it is a barrier to people, particularly outside of hospitals or academic medical institutions, to obtain these large sets in the U.S. In other countries, there's actually not as much in terms of protections for like HIPAA-like protections, or at least not as some countries are not as stringent. So I think in the U.S. particularly, we have possibly the most stringent patient privacy laws of any that I've ever heard of, which I think is good. It's a good thing.
Okay. Esther, thank you so much. We haven't been able to get through any of all of the questions here. Hopefully, we've covered off a number of them. I know there were any more, and if there are outstanding or burning questions, is there a way for people to reach you? Would you be
Sure.
kind of okay if people
Of
can
course,
kind of
yeah,
reach you an email and
yes,
so on?
yes, my email address I can put out. So let's see. Let's see if I get into the chat here. I just have a private chat. Okay. Well, I can give you my email address. So it's just my first name dot last name. Is there a way for me to write this?
If you go to the comments section, because I think you have private chat and comments.
I have
if you
private
click on
chat
comments.
Yes.
If you go to comments.
Yes. So it doesn't allow me to actually type any comment.
Oh, okay.
Let me just do this quickly. Sorry, I know we're running out of time here. I will just display my email address here. And yeah, any questions? Yes, please do contact me. Very exciting area. And what's exciting about it is, we've really just scratched the tip of the ice. It really is the tip of the iceberg. It's just unbelievable what can be done. And let me just share this. Can you see? Oops. Oh, sorry about that. Let me go to the end. Sorry about that. Where's that slide? Okay, sorry about that. All right, does that show up?
Yes, got it there.
Yes, okay, yes. Feel free to email with any questions. I'd be happy to hear from you. And
okay.
Yes, very exciting area for further work.
Okay. Wonderful. Esther, thanks so much. And for anyone who's interested, who didn't get your questions answered here, please take a note of that. And if you want to follow up with Esther, that's very, very generous of you that you'll give your time to that. So thanks everyone for your time on this first session in track 1. Esther, thanks so much. We're now going to move on.
Thank you so much.
Yeah.
Thank you.
Thank you.
Okay.
Okay, everyone. We're now going to move on. Before our next speaker, which is going to come up at the top of the hour, we're going to spend some time just connecting with each other. This is clearly something that we usually do face to face, but there's a way of doing this in the format that we've got here. To the left of your screen on Hopin, you'll see a networking tab. And if you click on that networking tab, what we're doing is we're basically connecting you with some other person in the conference for about 3 minutes, something like that. So you're able to just kind of connect with someone. You'll have about 3 minutes just to exchange thoughts on what's going on, or what you've learned over the course of the last couple of hours. And then after 3 minutes, you'll then go to someone else and network in that way. We'll run this for about 20 minutes. Just to give you the chance to kind of connect with whoever's in the conference. If you want to go over and connect with anyone in Wells Fargo. There's a lounges area where you can join the kind of connection lounge there. So if you want to be more specific about going to the Wells Fargo room, you can go there. Once the networking break is over, as I say, in about 20 minutes time, if you want to come back into track one, please feel free to do so. We're going to get a conversation and a presentation there from Megan Price, who's the Executive Director of Human Rights Data Analysis Group. That's where we'll be starting up back again at 2 p.m. Eastern, so at the top of the hour. 2 p.m. Pacific, sorry, at the top of the hour. So if you can go to the networking tabs now, enjoy yourself for the next 15, 20 minutes. And then if you want to come back to track one, we'll see you back here at the top of the hour. Thanks, everyone. Okay, welcome back, everyone. I hope you were able to connect with a few people in our short little networking break there. Hope that was a good experience. So we're back on track one. Thanks for staying with us if you were with us on track one a little earlier when we spoke with Esther, or welcome back if you're coming across from track two. So delighted now to introduce Megan Price. Megan is the Executive Director of Human Rights Data Analysis Group. She's going to be talking to us today about how data science and AI methods and tools are being used to build cases and answer important questions about the human toll of conflicts. So please join me in welcoming Megan to our virtual stage, and just give her a round of applause in the chat. Megan, thanks so much for joining us today, and over to you. And as I said to everyone as we've gone through this, if you have questions for Megan when we're talking, please put them in the chat, and then we'll do our best to get to as many of them as possible in a Q&A at the end of this. So Megan, over to you.
Well, thanks so much. I'm really happy to be here and really enjoying the conference so far. And I will try and leave some time at the end for Q&A. So hopefully I've organized myself correctly. So if we could just show my slides. Excellent. Thanks so much. So as that lovely introduction just mentioned, I am the Executive Director of the Human Rights Data Analysis Group, or HRDAG, as we call ourselves. And we are a team of data scientists who partner with human rights advocacy organizations to identify questions of fact or arguments that can be advanced through rigorous data analysis. And our work really wouldn't be possible without partnering with a wide variety of organizations. It really depends on the specific context and the specific project. But we've been so fortunate over the past 30 years of doing this work to work with everyone from large international organizations like Human Rights Watch or the United Nations to small grassroots non-governmental organizations in the specific countries where we have worked. Now, the starting point really for all of our work, I think, comes from this quote from my colleague and co-founder, Dr. Patrick Ball, that human rights stories tell about the worst events that anyone can experience. Taking responsibility for human rights information means assuming an obligation to the witness, to the families, and to the victim. We are morally obligated to do the best work that's technically possible so that the victim's story is heard and believed. And we always start from that place, and we always hang on to that as the motivation for the work that we do, because we are data scientists. And so we do have a tendency to get into the weeds of a problem and think really hard about maybe a bug in our code and how to solve it, or checking the assumptions of some of our models. But we never lose sight of the reason why we're paying so much attention to those technical details is because we have accepted this moral obligation to do the best work that's technically possible. And so that's really the motivation behind our work. And I also like to start with this quote because I think of it as a little bit of a content warning. So just to give everyone a heads up that this is the topic that I'm going to be covering for the rest of my talk. I am going to be mentioning examples of some of the worst things that can happen to humans that are these human rights violations. Now, one of the specific examples that I think draws that line pretty clearly between the work that is possible and the stakes and the impact that we can have is when our team provides expert witness testimony in court cases. This is actually the minority of our work. It's not all that often that we're called on to testify, but I think it is one of the most tangible ways that we can see the impact of our work. So I just want to start with a couple of those examples. This first one is from Guatemala, where again, my colleague Patrick, who's in the upper right-hand corner, is testifying against General Efrain Rios Montt, who is in the upper left-hand corner and was accused of committing acts of genocide in the early 1980s in Guatemala. And what we were able to show with statistical analysis was that the relative risk for members of the Mayan population of being killed by the army was 5 to 8 times greater than their non-Mayan neighbors in the same geographic regions. And the lawyers argued, and ultimately the judges concluded, that that statistical pattern was consistent with ethnically targeted violence, and it was consistent with acts of genocide. And in fact, when the judges came back with their guilty verdict, they specifically said that Patrick's expert report confirms in numerical form what the victims said. And I think this is really the best that statistics can offer to this kind of work, is confirming and contextualizing and amplifying those vital stories that are told by victims and witnesses. One other brief example, again, this is Patrick testifying in the upper right against former president of Chad, Hissène Habré, in the upper left. And what he's showing in this case is the estimated crude mortality ratio for prisoners held in secret prisons under the control of Habré at the time. And what Patrick was able to show was that this crude mortality rate was comparable to that of POWs during World War II. And so again, during their finding, their guilty verdict, finding Habré guilty of committing crimes against humanity, the judges specifically said that the findings invalidate the contention of the defense that the detainees were receiving comparable treatment to the usual living conditions of the civilian population. So again, this is what statistics has the potential to achieve in this area of work. Now, the way that we do that is through a variety of analytical methods. I think like any other data scientist, we try to think of all of our work as coming from a broad toolbox and identifying which set of tools is most appropriate to a particular problem. And that may be rather straightforward descriptive statistics, or that may be more complicated modeling approaches. My plan for today is to give a fairly high-level presentation with a few different examples. I'm not going to get into too many technical details, but if folks do have technical questions, I'm happy to get into that during the Q&A. And also, I really recommend that you look at the tech corner on our website, which is where we provide a lot more detail about some of these analytical approaches. And we write all of these tech posts in Jupyter notebooks. And so they include code snippets and visualizations. And that's a great place to start for a little bit more detail if you're curious. But for today, I want to talk a little bit more about a specific example that I've been working on with various partners, looking at the number of people who have been killed in the ongoing conflict in Syria. And this is work that we've been conducting with the United Nations. This headline is from 2014, so by now it is quite out of date. But I also want to point out that this headline needs a few more adjectives to be technically accurate to what the analysis can actually say about documented violence in Syria. And that's because the way this work starts is through partnering with various Syrian civil society groups who are collecting information about individuals who have been killed in the conflict. This is a screenshot from the Violation Documentation Center. They're still active, but they have since taken down, they used to maintain a publicly facing database like this because this was part of their mission, was to name these victims and to tell their stories as much as they could. And so this is, for our purposes, for these kinds of projects, the data that we start with. And there are multiple Syrian civil society groups right now maintaining these kinds of lists of named victims who have been killed in the ongoing conflict. And so one of the first analytical challenges for us is to determine the best way to integrate these lists of named victims and to identify records that refer to the same individual victim. And one of the ways to do this, and I apologize if anyone in the audience is an Arabic speaker, I know when I mix English and Arabic in this way, the Arabic ends up backwards. But just to imagine, this is one of the ways that we can start to answer that question, is by looking at pairs of records and just asking for each pair, does this refer to the same person? Does this refer to the same victim? Yes or no? Another way to visualize that is, rather than comparing pairs, is through clusters. And this is a visualization output that's an option from one of the scikit-learn packages in Python. It's called a dendrogram. And we use it both for manual human review and then to make decisions about the tuning parameters for the classification models that we use to scale this particular part of our work. And so the question here is, how many different individual victims are described by this collection of records that has something in common? And for the tuning parameter, the question is, what threshold do we want to set for our classification model above which we will say those records refer to different individuals, and below which we will say group these all together in one cluster? And so that's about as much technical detail as I plan to get into today, but I do want to point you specifically to one of our technical blog posts, which is precisely as it is named, a geeky deep dive. If you want more details on specifically the approach that we use to answer this question of which records refer to which records refer to the same victim. And for folks who are familiar with or who've worked with record linkage or entity resolution in other applications, I just want to say specifically that in our application, we have relatively little information on which to make this decision. So we're really relying on the name and the date and the location of the death to make these determinations. So it is a rather challenging problem to identify and group these records in a way that feels as accurate as possible. Now, that's one whole step in the analysis process, but what that bit of analysis answers is how many uniquely identified victims have been reported to at least one source. And that has a lot more modifiers than the headline we saw from the United Nations, because of course the question that we actually want to answer is, how many people have been killed? And if we think about, I think I've lost my slides. Hi, I think I'm here. I think we're all back. So as I was saying, that particular analytical approach, the question that answers is, how many uniquely identified victims have been reported to at least one of these organizations doing this work? And the question that we're actually after is, how many people have been killed in the ongoing conflict? And if you think about violence and violent conflict, of course, named, identified, documented victims are going to be a subset of the total number of victims who have been killed in a conflict. And so we need to use our statistical tools to bridge that gap. And fortunately, from an analytical perspective, this record linkage step moves us in the direction of the next class of tools that we can use to estimate what's missing. So if we think about how we can organize the records once we have identified multiple records that refer to the same person, we can create this kind of incomplete contingency table where we describe what I think of as documentation patterns. So we describe the number of victims who have only been documented by source A, the number of victims who have only been documented by source B, by both A and B, and so on and so forth. And then the last pattern is the missing pattern, the number of victims who, based on what we do know, we can estimate we must be missing information about. And the way we do that is through a very broad class of tools called multiple systems estimation. And if you're curious to learn more about this class of tools, there's a great review paper in the Annual Review of Statistics and Its Applications by Bird and King. It talks about a number of different areas of application where this particular method is being used to estimate what hasn't been observed. This class of methods has been around for literally more than centuries. And so there are a number of different approaches, but modern approaches, there are some frequentist approaches, the log linear modeling approach. There's some Bayesian approaches. These days, our team primarily relies on latent class models. But whatever approach you're looking to investigate further, these are all written up as packages in R. So they're readily available off the shelf for starting to experiment with and apply to various problems. Now, the only other thing that I want to say about this particular piece of work is that I talked about what the data looks like when we start the project, and then using multiple systems estimation to estimate the number of victims whose stories we have not heard yet. But there's actually two different kinds of missing data, two classes of missing data that can occur in these kinds of problems. And I have completely neglected to mention one of them for the sake of time, and that is missing data that occurs about the victims we do know about. So if we know a person's name and date and location of death, but perhaps we don't know their age or we don't know their gender, then we need to use another set of tools called imputation methods to fill in that missing data. And if you're curious to learn more, I really strongly recommend my colleague Maria Gargiulo's technical vision talk from a recent Women in Data Science conference. It's available on YouTube. And I think she does a really beautiful job of describing the overall infrastructure that our team uses to address both of these kinds of missing data and then combine them all into a single analysis that results in rather robust estimates and an appropriate measure of uncertainty once we've accounted for all of these different challenges in the data. So with the little bit of time that I have left, because I do want us to have time for a Q&A session, I want to talk a little bit about using machine learning models for so-called predictive modeling. And I want to compare and contrast two specific case studies, one in which our team argues these methods are appropriate and can help, and one in which our team argues these methods are likely to do more harm than help. And so the first case is work that we've done with our partners in Mexico, where our partners at Data Cívica and Universidad Iberoamericana came to us really with a question. And in Mexico, because of the ongoing violence there, there's a situation where what are called fosas clandestinas, or clandestine or undiscovered graves, are found with some regularity. And these hidden graves are really anywhere outside of a cemetery where multiple bodies are found. And our partners wanted to know, is there a way to predict locations where these graves are more likely to be? Because one of the challenges of advocacy in Mexico right now is advocating to local government to allocate the resources to conduct investigations to look for these hidden graves. And so they really just said, could you build a classification model that could predict these likely locations? And we talked to them about what we would need in terms of input records and data to build that kind of model. And then we pilot tested it, and it turns out that it was possible for our partners to collect the kind of information we needed, and that the results were fairly accurate based on what our partners knew on the ground in the field there. And when we showed our partners this example from 2015 of the municipios or the states within Mexico that had the highest probability of containing thus far undiscovered hidden graves, our partners kind of said, well, that makes a ton of sense. That's where we know violence is happening. That's very logical. That's not surprising. But then they said something else, which was, this is a really useful finding to them, because it can be difficult and frankly dangerous to advocate for these investigations, to say, please, will you go look in these locations for these hidden graves? And having the distance of a scientific model, being able to say, it's not us personally suggesting that investigations happen in these places, but rather this machine learning model that these crazy scientists in California built, we don't know, it says maybe we should go look in these places. That little bit of distance was actually really useful to them. And so all in all, in very close collaboration with our partners, we've concluded that this particular application in Mexico is likely to be an improvement on the status quo. And I'll circle back to that in just a minute, but I want to talk a little bit now about a case where we think that's not true, and that's so-called predictive policing. And this is work that my colleagues William Isaac and Christian Lum conducted several years ago. And I think, frankly, their findings are generally considered to be well known at this point, not necessarily their specific work, but this finding in general that so-called predictive policing is in fact well named because it is predicting the behavior of police. It is not predicting crime. And what Christian and William in particular were able to show was using open data from Oakland, California. The picture on the left shaded in red are drug crimes that are known to police in Oakland. And the picture on the right shaded in blue is from a representative health survey using self-reported drug use across the city of Oakland. And what you can see is that when it's self-reported and it is a representative sample, people everywhere in the city use drugs of some kind or another. Whereas the drug use that is known to police is focused in a very specific small number of neighborhoods in Oakland. And so if you use the data on the left to build some sort of predictive policing model, what it's going to do is it's going to reinforce those existing biases in the records of arrest and records of activities that are known to the police. And it's going to result in over-policing of certain areas of Oakland that are not in any way representative of the actual drug use that the police are theoretically after. Now, we can certainly have a philosophical argument about, whether drug crime should even be a matter for the police. That's a different question. But this is simply looking at the specific modeling approach and the result based on the data that's available. Now, at this particular moment, I like to pause, and I apologize. My reference here seems to have gotten just a little bit garbled, but this is actually a reference from a criminal justice article from the 1800s, pointing out that police data is partial and selective and therefore should be considered grossly invalid for answering questions about variations in crime. And so I love this reference because it is a lesson that I feel like we have to learn over and over and over again, that just because the data change and just because it feels like we have more data these days, we still don't have the kind of information that answers the kinds of questions we have, at least not with naive analyses. We at least need to be a little more thoughtful about the way we take the partial and selective nature of the data into account. And so with that, I just briefly want to say, okay, what's the difference? How come we think that in Mexico it is an improvement on the status quo, and in the US it is likely not to be? And that's because, as we all know, these predictive models are going to make mistakes. And the question is, what happens when we get a false positive or a false negative? And in the case of Mexico, a false positive means that we might waste some resources. We might look in a place we didn't necessarily need to. And a false negative means that we have missed an opportunity. We probably have missed a chance to go conduct an investigation for a gravesite. But neither of those, in close collaboration with our partners, is considered to be worse than the status quo. Whereas in the predictive policing model, a false positive means that a neighborhood can be systematically over-policed. And I think at this point in the US, we have seen the incredibly negative consequences that can have on individuals and on communities. And so again, this is really the point that I made on the last slide, that we know our machine learning models are going to be a little bit wrong. Otherwise, they're not actually helping us. They're not actually telling us things we don't know. And so we need to think really hard about what are the ways in which they're going to make mistakes? Is it more important to our substantive question that we prioritize and worry about false positives or false negatives? What are the reasons why we think we might get one or the other, or more of one than the other, based on what we know about the characteristics of the data that we have available to us to build those models? And remembering that in these kinds of social applications, by definition, the data that we have available to us are very, very, very messy and complicated. And so I just want to close with the way our team makes these decisions about not only what tool in our toolbox to use, but whether we think these particular data science tools are appropriate to a particular field of application. And the question we ask ourselves is, what's the cost of being wrong? Are we going to waste some resources, as the case in Mexico, or are we going to affect people's lives? And who bears that cost? Is the cost going to be borne by us building the model, by an organization that is allocating resources, or is it going to be borne by the people on whom the tool is being imposed, and people who may not have had any sort of input or control over the development of that particular tool and the interpretation of its results? And so I really encourage all of you who work in this field and who are considering working in this field to really think about that question when you are presented with opportunities, because obviously as a data scientist, I think these tools are incredibly powerful and I think they should be used. But I think that we really need to think about this question of what could happen when it goes wrong and who might bear that cost. And with that, I will stop and say thank you so much. There are many ways to get in touch with me, to follow HRDAG, to learn more about the work that we're doing. And if I have timed it right, I believe we have just a little bit of time for some Q&A.
Great. I think we have. Megan, thank you so much for that. Important questions and important messages there. And you have timed it right. We've got about 5 minutes left for Q&A. I can see a number coming up here. Let me highlight one from Mark Kraus there. Mark asking, I don't know if you can see it in the comments, can you speak to why finding locations of clandestine mass graves might be more accurately estimated with a latent model rather than with Bayesian inference?
Oh, that's a great question. And I apologize. I think probably I didn't make my transition from one kind of method to another very clearly. We're using the latent models for the multiple systems estimation application. So when entire records of victims are missing. In the Mexico work where we're predicting the location of graves, we are using pretty straightforward classification models. In fact, in that case, we found just a random forest is as accurate as sort of more complicated classification options. But I think in that particular application, it's really question specific, which sort of set of classification tools is going to work best. I don't think there's a particularly strong theoretical reason why, for example, random forests in this case worked better for us.
Okay, Megan, thanks. There's a couple of others I want to cover in the last few minutes here. This can go in a lot of different directions, but interpret it as you wish. Alyssa asked a question, would love to hear more about how you approach the role of power and control in your work.
I love that question because we really think that is one of the things that data science can provide is a real lever to push against some of the power imbalances that exist in so many of the fields where we work. And so that's one of the things we really try and talk about explicitly, especially in our work in the US. And especially, I'm thinking we have a partnership with an organization in Chicago called the Invisible Institute. And we really bring our partners in, and it's not just, I'm not paying lip service to collaboration. We really couldn't do our work without our partners. And so we think their expertise in the field that they work in and in the specific context that they work in is every bit as valuable as our technical expertise. And part of our job is handing over some of that power and really working as equals. And so one of the things that my colleague Tarek Shah, who leads that work in Chicago, I think has done so beautifully with the Invisible Institute is it's a team of local volunteers in Chicago who create all of the training data for the machine learning models that we use in Chicago. And that team of volunteers really they determine what is important to their community. They determine what it is those machine learning models should be classifying, should be predicting, and we trust them and we believe them. And so I think that's one of the ways that we as data scientists can kind of use our tools to push against power imbalances.
Great. And maybe just a final question, which I think in some ways segues nicely with that. There's a question from Henry here. It looks like there's a ton of data science for social good type organizations. Is there an overarching method of coordinating and communicating across there? What's your sense there? You can read it on the screen.
Yeah, gosh, I wish there was. And I definitely, I mean, especially, you know, this conference is being hosted at Berkeley and I'm based in San Francisco. I think especially here in Northern California, right next to Silicon Valley, you're completely right that there's just, we're sort of awash in X for good. It might be data science, it might be artificial intelligence. And I don't really know how best to sort of organize that, to give that some more infrastructure. One of the things that I've been advocating for when I am on the talking circuit, especially when I have a university in front of me, is that more data science institutes should be stepping into some of those leadership positions. And so I'd love to see more university-based data science schools and institutes partnering with human rights centers and sort of providing some more of that infrastructure and coordination.
Great. A challenge and an opportunity there. Megan, that's great. Megan, thank you so much for joining us this afternoon. Really, as I say, kind of powerful, important messages and just important work that you're doing. So thank you for sharing that with us.
Thanks so much.
All right. Okay, everyone. Thanks for your questions and for listening in on that. We're now going to move to our last speaker here on track one for the afternoon. This is Josh Blumenstock. Josh is an associate professor here at our UC Berkeley School of Information, and Josh is going to be talking to us today about the work that leverages innovations in machine learning to tackle problems affecting poor and marginalized populations. So. Josh, I think you're with us, and what we'll do now is, as I've done with the rest of the participants, again, Josh will have about 20-25 minutes to present, and then we'll keep 5 or 10 minutes at the end for Q&A. So as Josh is going through his presentation, if questions occur to you, or if you want to put comments in the chat, please do so, and then we'll have the chance to reflect on some of that towards the end of the presentation. So with that, Josh, thanks very much for joining us, and the floor is yours.
Great. Thanks, Jonathan, for the introduction. Apologies, there's a protest on UC Berkeley campus right outside my office right now. So if you hear that, that's what's going on. But what I'm going to talk about is some work that I've been doing over the last couple of years that is trying to use new sources of data and new approaches to data science to combat issues of global poverty. I'm going to talk primarily about joint work with a PhD student named Emily Aiken here at the iSchool, as well as a PhD student, Suzanne Ballou, at University of Mannheim, and then 2 faculty at the Department of Economics at Northwestern University, Dean Carlin and Chris Udry. But just to make sure we're all sort of on the same page in terms of context, I think it's important to note that, look, while the COVID pandemic has really had terrible consequences everywhere, it's really reached a crisis level in a lot of developing and impoverished countries. And the key difference there is that you have very large populations that even prior to the pandemic were living at, below, or maybe just above subsistence levels. And then when the pandemic arrives in the country, there's not just the health consequences, but there's the economic consequences. And so what a lot of countries did was put in place lockdown orders, curfews, and so forth that prevented people from working during the day. And so when you have a very poor population, you remove away their primary source of income, then this really quickly translates into food security and extreme poverty. And so if you look at a global scale, it's a little bit distressing because over the last several decades, the world has made actually remarkable progress in reducing rates of extreme poverty. But then, starting in late 2019, there was actually a sharp uptick in global extreme poverty due primarily to the COVID pandemic. So the most recent estimates I've seen suggest that about 100 to 150 million new extreme poor now exist as a consequence of the pandemic. So that's sort of the specter. On the other hand, there has been a really remarkable global humanitarian response to this crisis. So globally, about 3,300 new social assistance programs have been launched since 2020. Collectively, these are providing over $1 trillion in cash payments to something like 1.5 billion people. So that's over 1/5 of the world's population. But what I want to talk about is a key challenge that's faced by each one of these social assistance programs, which is the question of how do they decide who should get the resources that exist? Because all of these programs have finite budgets, they all operate under real world constraints, and so they don't have enough money to pay everyone. And so the program administrators have to make tough decisions about whom to prioritize for cash transfers or other resources. And look, this is a challenging problem everywhere. It's a challenging problem in the United States. The CARES Act was a little bit controversial, the way that targeting was determined, but it's a particularly difficult question in low resource environments where you don't have the sort of data sets that anti-poverty programs typically rely on in order to make these decisions. So, for instance, in the United States, the US government looked at tax return information to make assessments over which households had an annual household income below a certain threshold. I think it was $190,000. But if you look at Somalia, Congo, Eritrea, none of these countries are places where people are really reporting much in the way of income taxes. A lot of income is informal or it's subsistence agriculture. And so the government as an administrative entity just doesn't have good insight into who has the greatest need for humanitarian aid. So what I want to talk about for the next 15 or so minutes, the key takeaway is that in some circumstances, not all circumstances, but in some circumstances, new sources of data and data science machine learning methods can improve the targeting and delivery of humanitarian aid. So, briefly, I want to give a little bit of background on the specific context where our work took place, the country of Togo. Then I'll do a couple of methodological dives into some of the machine learning methods that we used, and then I'll provide you some of the details on the evaluation we did in Togo to assess the extent to which one method might actually work or might not work. And then towards the end, I'll step back and mention what I think are really critical non-technical considerations, like not just data science or machine learning, but really the social, ethical, and practical considerations involved in these sort of applications of machine learning. Okay, so Togo, it's a small country. You can see a map of West Africa here. Togo has about 10 million people, about 6.5 million adults. Although one of the things we'll come to is that no one actually really knows how many people are in Togo because the state of data quality is so low and out of date. It is one of the poorest countries in the world, even pre-pandemic. I think the best estimate is that the national poverty rate was somewhere between 55 and 60%. So very pervasive poverty. And what happened in Togo is similar to what happened in a lot of sub-Saharan African nations around the time of the pandemic, is that the first COVID cases arrived, relatively late in the grand scheme of things in early 2020. And so in Togo, they were in March 2020, and then pretty soon after the first cases arrived, the government launched a humanitarian aid program called Novisi, which is the local language for solidarity, that they used to distribute cash payments of about $10 every 2 weeks for around 5 months to eligible beneficiaries. The program was remarkable in several respects, one of which was that it was entirely digital. So you would register using your phone and you would receive a cash payment using the phone. And this is important because there's no other electronic currency system that is pervasive in Togo. And it was totally infeasible to imagine the government mobilizing a massive in-person cash or food aid distribution program in the middle of the crisis, particularly because, rewind, put yourself in your March 2020 mindset, no one really knew how the virus was spread. And in particular, the notion that it could be passed through surfaces and through the exchange of goods and bills was still quite common. So they launched this program. There's this little video that they used to promote awareness of it, basically to sensitize people to the idea that if they registered, they could receive these cash transfers directly to their phone. And then once the cash transfer was made to their phone, they could cash it out with any local business or buy basic goods and services using the money on their phone. And it doesn't have to be a smartphone with a banking app. It could any old feature phone, a $10 phone would allow for receipt and exchange of this money. Okay, so that's the system. But the challenge was they didn't have a really good way to determine eligibility. So I mentioned that there were about 6.5 million adults. In the particular phase of the program that we were working with the government on, they had about $10 million, which was enough to provide transfers to about 100 to 150,000 individuals. So a relatively small slice of the total population of Togo. And not only did they not have information that would tell them which individuals were poorest, they didn't even have information that would tell them which villages or cantons or prefectures are the equivalent to counties or states were the poorest. The most recent data set that was nationally representative in Togo was collected in early 2019. And this is showing you a map of Togo with all of the cantons, or again, think of them as counties, where in green, I'm highlighting all of the counties where one or more households were surveyed. And in gray are all the cantons where 0 households were surveyed. So what this means is if the government is trying to determine whether or not they should prioritize the villages in this canton that I'm highlighting, they don't have any data that tells them about the living standards in that particular canton. And this predicament is not uncommon. This is, you can see in these statistics, less than half of the poorest countries have completed a census in the past 10 years. So what this means is a lot of governments are facing very similar quandaries as the Togolese government. Okay, so how can machine learning and big data potentially help? Well, I think the first idea is very intuitive, which is that wealthy regions around the world look different from poor regions. And what I have here are 2 high-resolution satellite images, one of Mexico City and one of Cape Town. And note that I'm not like stitching together 2 images. This is just one particular image where you see a very sharp, stark juxtaposition of relatively affluent people living next to relatively impoverished people. And same thing is true here in Cape Town, South Africa. And what I want you to take away from these figures is these images is that even though probably most of you haven't spent a ton of time in Mexico City and Cape Town, just by looking at these images, you can sort of tell that the people living over here are wealthier than the people living over here. And so then the question is, can we train a machine, basically a computer algorithm, to learn those differences? And there's been a series of papers and results that indicate that in general you can do this. And the intuition there is that, as I'm guessing many of you know, machine learning algorithms are really just sophisticated technologies for pattern recognition. And so if you can train the machine learning algorithm with reliable representative data, it can learn to detect those differences. And so the idea, I'm not going to talk about the details, but if you're interested, we can go through them in a Q&A. The idea is that the machine learning algorithm, these deep convolutional neural networks, trained on reliable ground truth measures of household welfare, can learn to pick out the differences, the signals in the satellite imagery that are indicative of relative wealth and poverty. And so what we do is we use these algorithms to go from the high resolution satellite imagery to high resolution poverty maps that look like this. And from there, we can answer the questions of the Togolese government about, like, okay, this particular canton here, where do we think it falls in the relative wealth ranking of all of the cantons in Togo? So this was sort of step 1 in the process that the government used in determining how to expand their humanitarian aid program across the country. They wanted to start by rolling out to the poorest cantons, and they used these satellite-based poverty maps in order to make those decisions. Okay, so that's the first step. The second step, and this is where it gets a little bit more interesting, was the realization that, okay, even if they're going to prioritize, say, the first 100 poorest cantons for this $10 million program that they had, there's still more than 1 million people living in those cantons, and they don't have enough money to provide benefits to everyone. So how do they determine whom should receive benefits even within those 100 poorest cantons? And for the record, they could have made a different decision and said, okay, let's just pick the 8 poorest cantons and give money to everyone in those 8 poorest cantons. But then, of course, you're leaving out everyone in the rest of the country. So, these are one of the decisions that the government was trying to make. And our research team helped provide them technical advice to figure out what would make sense for their particular questions. So one of the things that we also documented was the notion that data from mobile phone networks and mobile phone companies can provide a useful proxy for the socioeconomic status of individual mobile phone subscribers. And now there's a simple insight here too, which is very much like the satellite data, where wealthy regions look different from poor regions. wealthy mobile phone subscribers use their phones differently than relatively poor mobile phone subscribers. This is something that's true not just in Togo or West Africa, but it's true around the world, including in California and the United States. Wealthy people, they own different types of phones, they have different data plans, they have different apps installed on their phones. And if you look at Togo, the differences are a little bit more basic. Wealthy people use their phones more frequently than relatively poor people. And there are literally hundreds of different metrics of phone use where you see pretty striking differences in patterns of activity between the relatively wealthy and the relatively poor. And the idea here is to use machine learning algorithms to take these signals and turn them into a prediction about whether or not a given mobile subscriber is above or below a particular poverty line. And so, as with the satellite data, the key is to have reliable ground truth data. So this is like my one quick digression into the methods of how we actually do this, just so you have a taste for what it looks like to do this research in practice. So what we did is we started by conducting a large survey. And we did this survey, it was designed to be representative of the population in those 100 poorest cantons where the government wanted to expand the program. So we called a representative sample of about 15,000 individuals living in those 100 poorest cantons. During the process of the survey, sorry, this slide is actually from a project in Afghanistan that predated the work in Togo, but this intuition holds for Togo as well. The idea is you speak to these thousands of individuals. Over the course of that conversation, you go through a process of getting informed consent to make sure that they're interested and willing to participate in the research study and to relinquish access to the particular data sets that we're requesting in order to undertake this research. But assuming that they participate, through the survey, you get what I will call gold standard measures of the welfare or the socioeconomic status of the particular individual. And just a footnote here, there's great debate within the economics and sociology and development communities about how to best measure welfare or poverty in a context like Togo or Afghanistan. What we do, or what we try to do, is take the state-of-the-art methods for measuring household welfare in a survey and use the surveys to elicit that measure, which I'm going to call YI. So basically, for every person that we conduct a survey with, all 15,000 of them, we have a label that tells us the ground truth measure of their wealth or poverty. Okay? Then at the same time, we work with the mobile phone companies to get access to the metadata or the call detail records from that particular individual's phone, again, with their consent. The metadata are not the contents of the call or the transcripts of the text messages that they're sending. It's basic information like that says, for instance, this particular phone number made a phone call to this particular phone number at this particular time, and then we know the cell phone towers that the call was routed through. So it allows us to roughly place the person at the time the call was made within like 1 or 2 kilometers. From these call detail records, we can then engineer a bunch of features. We can make a bunch of different measurements of how this particular individual is using their phone, the number of international calls they're making, the number of text messages they're receiving, and so on and so forth. And these are what I'll call the features or the predictors XI. So now, for all of the people that participated in this survey, all 15,000 of them, we have a measure of their ground truth socioeconomic status, and we also have a vector of a large number of measurements of how they're using their phone. And then it's a pretty standard machine learning exercise to say, to what extent can we predict socioeconomic status Y given measures of phone use X? And so we fit a model, which I'll denote by F, that allows us to then predict for each of these subscribers what their ground truth wealth status is. And the key advantage here is not that we can do this for the 15,000 people who participated in the survey, but that there are 6.5 million people, or sorry, I should say about 5.5 million mobile phone subscribers who are using their phones, who it would be infeasible for us to actually survey. And for those people, we can have an estimate of their socioeconomic status. And so what does it look like at the end of the day? If you focus on this figure at the right, this is the one that I've been talking about, where we conducted this survey in September of 2020, immediately prior to the expansion of the Novisi program in October of 2020. And what you see here is I'm plotting the true socioeconomic status of the individual on the x-axis. So this is denoted in dollars per capita per day consumption against our machine learning model based on cell phone data prediction of that same individual's socioeconomic status. So there's 15,000 dots here, one for each of the individuals in our training data set. And you can see that there's a relatively decent correlation. So this particular model explains 35% of the variation in actual socioeconomic status. And it's far from perfect. And I'm not trying to claim that there's not a lot of error in these predictions. What I do want to point out is that there is some signal in this phone data machine learning model of underlying socioeconomic status. Okay, then the real question is that signal that we see in the, sorry, I want to say one other thing. This is not something that we've only documented in Togo, but it's a finding that has been replicated in several different countries and several different points in time. In general, as I was saying 5 minutes ago, it's generally true that mobile phone data, patterns of phone use are indicative and predictive of socioeconomic status. Okay, but then the question I want to turn to is this signal, is this enough of an accurate prediction that we might want to use this to make really important decisions about how to allocate and target humanitarian aid? And to answer that question, I want to show you one more figure, which is this one here. And this is a little bit more nuanced than the last one. It's basically the same scatter plot in the background. But here I want to illustrate to you what it actually means to use this for targeting. So the government, and sorry, I'm denominating now in the local currency, not in dollars, but the government had a fixed budget of $10 million. And that meant that they could help a fixed number of people, call it 100,000 people. In principle, what that means is they want to provide transfers to everyone below a particular threshold in consumption or in poverty, right? So they want to target everyone on the left side of this vertical dashed line. But the government doesn't actually observe the true consumption of anyone because they don't have the data. So if they're going to be using this mobile phone data prediction model, in practice, they're going to end up targeting along the y-axis, the vertical axis, which means that they're going to target everyone below some horizontal line. And so this allows us to say something about the inclusion and exclusion errors in this particular targeting algorithm. In particular, we're really worried about the dots in this upper left-hand quadrant. These are the people who are truly poor, in other words, to the left of the vertical line, but the algorithm predicts them to be above the poverty line. And so these exclusion errors as well as the inclusion errors are what you want to minimize. And by contrast, you want to maximize the number of observations that fall into this quadrant and this quadrant. And now, if you look at this figure, you're probably thinking, and you should be thinking, hey, there are a lot of dots up in this quadrant. And it's absolutely true. And so is that a concern? It certainly is. But the real question is, are the exclusion errors that are created by this particular prediction of consumption better or worse than the exclusion errors that would occur if the government were to use other possible options for targeting humanitarian aid? And so this paper actually was published last week in the journal Nature. Most of the paper is devoted to answering that question. And so I'm going to just show you one figure from the paper that I think conveys the key intuition here. So what I'm showing you here is in the green bars, I'm quantifying the performance as measured in exclusion errors, as well as a couple other technical measurements, area under the curve, precision and recall, of 4 different approaches. The phone-based machine learning approach is shown in green, and I'm comparing this to a geographic targeting approach and an occupation-based targeting approach. And these are important comparisons because these are the 2 other options that the government had at the time in Togo. In particular, they could have done what I mentioned earlier, which is instead of prioritizing the poorest mobile subscribers in the 100 poorest cantons, they could have just prioritized every single mobile subscriber in 8 cantons. But if you do that, you miss a lot of poor people that live in those other 92 cantons. And that's why you see relatively low performance of this geographic targeting approach. Another option that the government was actually considering at the time was to target based on occupation. So I didn't mention this, but there had been a voter registry. There had been a national election in early 2020. In the run-up to that election, they had updated their voter registry. So the voter registry, sort of coincidentally, had information on people's occupation. And so one thing they considered was targeting specific occupations, basically people who registered to vote in specific occupations that they thought would be particularly vulnerable. But what we see here is that also doesn't do a great job at prioritizing the poor. And so look, the moral of this story when looking at this figure is not that the phone-based approach is wonderful, but it was the best of the available options. So in practice, that's what the government actually ended up using for this particular phase of the expansion of the Novisi program. I'm pretty much done. I just want to briefly mention a couple other areas that I think are really important that we look into in detail, and I'm happy to talk about in the Q&A. One is, remember all those dots, those exclusion errors that we're particularly worried about? It's important to note that while the machine learning algorithm was a really important and significant source of exclusion errors, there were a lot of other elements of the socio-technical design of this particular paradigm of aid distribution that also caused exclusion errors. One thing that you're probably wondering is, what about the people who don't have phones? Well, we do a lot of analysis of that. Our best guess is that about 15% of the population doesn't have easy access to a mobile phone and might be systematically excluded. Likewise, there was a requirement that each beneficiary be registered to vote, and this was important to the government because they wanted to be able to ensure that no single person could register twice. And because there's no common national ID system in Togo, the voter registry was what they used as a way to uniquely identify beneficiaries. Another really sort of important and unexpected source of exclusion errors was the fact that people had to actively make the decision to register. They had to learn that the program existed, and they had to dial the numbers on their phone in order to register to receive the transfers. And this actually excluded a large number of people. So again, broader point that there's a lot of focus, rightfully so, on systematic exclusions caused by machine learning algorithms, but just pointing out that there are also very important systematic exclusions from other elements of program and policy design. Let me skip this in the interest of time and just close on this last slide, which is to say that, you know, so far I've mostly focused on trying to convince you that this particular method that we used, that the government of Togo ended up using in late 2020 was accurate relative to other methods that they could have used in terms of minimizing errors of exclusion. It's also probably pretty intuitive that it was fast and cheap relative to other methods that would require, you know, massive data collection and in-person distribution. So, you know, our takeaway here is that in the context of a crisis, when time is of the essence and the outside options are really limited, we think this is a policy tool that it's worth like adding to the set of possibilities. But it's far from perfect. And in particular, I think it's important to point to, if not discuss in more detail, what we consider to be some of the real important issues to think about, both in the context of Togo, but especially looking to the future, if these methods are going to be used more commonly in the design of humanitarian aid and crisis response systems. How do we think about exclusions of people who don't have phones? Is there a way to provide backup registration and payment mechanisms that can get them cash? How do we think about data access and data privacy? I haven't mentioned this at all just because it's only a 20-minute talk, but the data coming from the mobile phone companies is very sensitive and it's personal data, and we don't want just anyone having access to the data. So can we design a system like this that has privacy guarantees through differential privacy or institutional safeguards that minimize the extent to which different parties are accessing different types of data? We did a lot of that in Togo that I'm happy to talk about in the Q&A, but I think this is a more general concern that's worth debating. What about questions of algorithmic biases and the worry that non-representative data or even representative data could reify existing biases? We do a lot of analysis of this in Togo, but again, the results may be specific to Togo. What about informed consent? Are there mechanisms for appeals and recourse? And some questions that came up at the end of the last talk. How about the notions of power and disempowerment that occur when you have a centralized algorithmic system for distributing aid relative to, say, a bottom-up community-driven system for distributing and targeting aid? You know, these are very important policy considerations. And finally, how do we design this policy? I mentioned institutional safeguards, but in a way that ensures that the same methods and data can't be used in ways that are not sort of coherent with the original design and intent of the program. I think the bottom line takeaway here is not that this is a silver bullet, not that every program in the future should use machine learning and mobile phone data, rather that it's worth considering this as one amongst many options, and really where the research frontier is now, and what I and my team are working on very actively, is how to think about best integrating multiple approaches to targeting to have sort of a complementary integrated system for social protection that minimizes different types of exclusion as a coherent whole, rather than just one or the other options. Final slide, I'm going to just put this up here, is I think really good motivation for this broader line of work, which is just to point out that there's so many billions, probably trillions of dollars spent annually on using machine learning in financial services and advertising, and a lot of things where, you know, small increases in area under the curve or predictive accuracy can produce large financial returns. I think we just want to point out that there's huge human returns to adapting these methods to use cases where, you know, predictive algorithms can actually have a positive impact. So with that, let me close. I'll pass it off to the moderator to help me sort through some of the comments. I see there's a bunch. I haven't read any of them. So I look to you for guidance. I'll just sort of put up this picture of the team. This is Emily and Suzanne, who I mentioned. Contact information here. And if you're interested in this topic more broadly, I teach a course at Berkeley called Big Data in Development. And it's all the materials are online and available for free. So go ahead and take a look if you're interested. There's lots of links and references there. So thank you. I'll leave off.
Josh, thank you very much. Yeah, that was great, and lots of comments, lots of interest there. We've only got a couple of minutes, so we won't do justice to all of these, but I will maybe guide us through a couple here. So maybe I'll turn first to the question from Naga there, Chandrasekhar, and will such tools be available, do you reckon, to individuals and smaller organizations for use for distribution directly to individuals? And then some of the things that you addressed in the last few slides, ethical and legal implications for using the tool at an individual donor level.
Sorry, didn't quite catch the second part of it, but let me start with the first. Oh, I see it right here. It's on the slide in front of me. Yes, so actually good timing. Last week, my team, in collaboration with Give Directly and with grateful support from Schmidt Futures and the Rockefeller Foundation, released an open source version of this software. Basically, we spent a lot of time taking all the code that went into this particular project and that we released as part of the transparency and replication process for the journal into something that's much more user-friendly. We also work with the UN Office of Humanitarian Affairs to have them review the sort of ethical and privacy considerations to make sure that there weren't any snakes in the grass that we hadn't thought carefully about. And this is all now out in you can find it through my lab's website right here. Also on Twitter, actually just recently I tweeted the link to this particular code repository. And then the second part, ethical and legal implications. So that's a real can of worms. It's going to be hard for me to address in 2 to 3 minutes, let alone 20 seconds. But I think the big lesson is that the ethical and legal implications are all entirely context specific, and it's really hard to address them in the abstract. But just to sort of make sure that in the particular context of Togo, there was this humanitarian crisis. And so I think there is doctrine around humanitarian response about what are sort of necessary and proportional uses of data. And so we kept those in mind. And I think those broader frameworks, and I'm not sure if there's an easy way for me to circulate links, but on this course syllabus, there's a module on ethics and privacy. And in that, I linked to several different frameworks that people who have put a lot of thought into this exact question have put forth as ways to think about how to responsibly use data in machine learning in the context of a crisis or for, quote unquote, social good purposes.
Okay, great. I think we've got time maybe for just one final question here, Josh, and I know there are a number of others, and I'm sure people will be following up with you, and thanks for giving contact details. Maybe I'll leave the last one there. There's a couple of questions from Alyssa. talking about similar efforts within the US. So let me take the kind of the second half of that. Do you see any opportunity for parallel work within the US, targeting services aid? What kinds of data beyond administrative data might be useful to look to?
Yeah, I think there is very similar types of work in the US. I think the exact sort of data sets and models that we used in Togo are likely to be different, partly because the administrative data capacity in the US is, orders of magnitude greater than in a country like Togo. So while the CARES Act has been a little bit controversial and the use of income tax returns has also been controversial, it is relatively reliable. So the margin to improve upon it is much lower than the margin to improve upon the options that existed in Togo. That said, there's been a lot of work that's using high-resolution satellite imagery to measure welfare and vulnerability in place in the rural United States. There's also a lot of work that I've seen where people are trying to compare how the combination of a bunch of different administrative data sets using machine learning methods can provide a higher fidelity reflection of a person's true vulnerability or welfare than relying exclusively on a single data source. To my knowledge, none of those methods have been used in policy, but they're starting to exist in the research literature. And my experience in Togo is that things have to exist and be documented extensively and validated in the research literature for at least a few years before it makes sense to start testing these in policy. So, I haven't seen anything yet, but I wouldn't be surprised if it started to come out in the coming years.
Okay, great. Have we got time for, Josh, have you got time for one more question?
Yeah, I can try and be quick.
Okay, great. I want to just highlight, Spencer, you've got a couple of questions in there, and I just want to highlight the first ones of those. You're talking about working on a similar project to estimate local populations to guide polio vaccine distribution. Some suspicions in there about data we collected underestimated populations. And I don't know whether you might have talked a little bit about this, Josh. Anything coming up from the Togo work there? Did you find you had similar issues when the validity of the ground truth was in doubt?
Yeah, so I'll say two things. I think one, you're absolutely right. And it's been documented in so many cases, but that if your training data are not representative of the population of interest, then your machine learning is just going to reflect the biases that exist in your training data. So it's great that you were clued into this in your project. In the Togo project, we did two things. First of all, we used 3 different large survey data sets to sort of corroborate the findings across them. The other thing is we had the opportunity to design our own survey. And this was really important because we wanted to make sure, as I mentioned, that our predictive model was trained on the sample of subscribers coming from those 100 poorest cantons. And we wanted to fit the model as close in time to the model's deployment as possible, because we were worried that, yes, mobile phone data are predictive of wealth right now, but my mobile phone patterns might change over time if there's a pandemic or if there's a promotion on international calls, and we didn't want that distortionary behavior, sort of that Lucas critique, to apply. So the other thing we did is, because we were able to collect our own data set, our own survey, we were very careful in how we drew the sample for it. And we used methods from adaptive sampling and online learning to oversample the particularly underrepresented subgroups, so that we could then make sure that because if you have an underrepresented subgroup, even if you have a representative sample, you just won't have a lot of data from those subgroups. So that was one thing we were able to avoid because we had control over the survey. But more generally, to Spencer's point, if you're just taking found data, I think you have to be especially careful that it's actually representative of the sample that's of interest.
All right, very good. Okay, we've come to the end of our time. Josh, thank you so much for spending time with us this afternoon and sharing some really important and interesting, and I think groundbreaking work there. So thank you for that. For everyone, this is the end of DataEDGE for 2022. 3 hours, but I think a very, very rich conversation that we've had here, both in terms of keynote and a number of other conversations in the tracks. So we're very, very grateful. Thanks so much for joining us all for this year's DataEDGE event. We can't wait until next time, maybe virtual, maybe in real life as well. So really appreciate you joining us. Thanks very much for the questions. And I'm sure there will be follow-ups from the organizing team. And if you need any further information, you can certainly get that from the team. Or if you want to follow up with any of the speakers, we'll be able to arrange that as well. Thanks very much for your time today, and we'll now sign off. Thanks now. Bye-bye.